Today we will be going over limits of linear regression, so the extent to which you can infer from linear regression models. The reading for this lecture is Chapter 3, Linear Regression, from An Introduction to Statistical Learning with Applications in R. If you have not yet read this, please pause, go read this, and come back. This lecture has two primary topics. One, interpretation constraints of ordinary least squares regression, and two, pitfalls of linear regression as a tool. First, we'd like to focus on interpretation constraints. In prior lectures, we went over the two general goals of trying to learn a function f that relates your inputs, x, to your output, y. In the fundamental form of any statistical model, learning f is your primary goal, but how you use f, how you take away from what you learn from your model fits, can vary. In some contexts, your goal should be inference, trying to understand how x or changes in x associate with changes in y. In other contexts, you might have a prediction goal, in which you're trying to predict a future observation in y from x. So in some cases, you're trying to gain intuition about the relationship between x and y, a deeper understanding of the nature of that relationship. In other contexts, you're trying to maximize control over y. You're trying to come up with a tool that will predict future y's, that has generalizability. Now, these aren't mutually exclusive, and we will keep going into ways of looking at the model that you learn that gives you both inference and prediction. But in this lecture, I'd like to focus a little bit on how we typically approach these two problems, or two goals of f, inference and prediction, in the context of linear regression itself. Let's consider the context of inference, where you want to fit a regression model in order to gain some inferential understanding about the relationship between x and y. Let's consider the case where you want to understand what factors associate with house value. Let's say you have a data set where you have an estimate for the median house value of a particular neighborhood or block. You also have information about local crime rate, the number of houses over 80 years in age, local property tax rate, the student-to-teacher ratio of local public schools. With this information, you could construct a linear regression model to predict median house value from these independent variables. And if you run a regression fit in something like R, you will see a table that looks like this. Often this is the primary summary of output that you'll get in tools like R. So every row is now the result of a specific factor in your model. The intercept is the beta naught term. You have your crime rate, you have your house age, tax rate, student-teacher ratio are all separate rows. Each column represents a summary of a model fit term from that model above. So your first column here is just the regression coefficients themselves. The second column is your standard error of those regression coefficients. The third column is the t statistic, which is the ratio of the regression coefficient over the standard error for that regression coefficient. Then you have a p-value, which is estimated from the t statistic, and a column typically that indicates whether or not a particular term is statistically significant. Now, the way that you would use this model to gain inferential understanding is by looking at which terms are statistically significant in terms of their association with house value. So in this case, crime, the tax rate, public school student-teacher ratios all seem to be statistically significant in terms of associating with y. House age, on the other hand, used by the proxy of the number of houses in the neighborhood over 80 years old, does not seem to associate statistically with house value. Now, when we say associate or does not associate statistically, What we mean here is that we are fairly confident that the real effect or the real regression coefficient for a term is not 0. Because there is some error associated in these fits, which is shown in the standard error column, we know that the mean value might not be accurate. So we get an estimate of the range of those regression coefficients. And if that range does not include 0, based off of some a priori confidence level, let's say an alpha of 0.05, then we say that we are confident that it is non-zero, either positive or negative. And that's how we typically use inference in psychology and neuroscience. We just ask which terms are statistically associated with y, and we gain an inference. So here, we feel fairly confident that crime, tax, and student-teacher ratio are very important in determining house value, but the house age itself, at least using this measure, is not. Now, this is different than, say, asking the question of what factors predict house value. Now, you'll notice for the prediction question, the model still looks the same. The form of the regression model itself looks the same. Really, the difference is in how we use it. Rather than asking whether or not individual regression coefficients are statistically significant from 0, what we want to do is use the regression coefficients that we fit to predict unseen values of y. So in this case, maybe we fit our regression coefficients on a subset of data from, say, Boston, and using the regression coefficients we get from Boston, try to predict the house values in a city like New York or Pittsburgh. Now, the typical way that this is done is by having your data set broken up into 2 different parts. So let's say this is your data set where you have n observations and p variables. In this case, we have 5 variables. What we're going to do is we're going to split this data set in half. The first half we'll call our training set. So we'll have a new y and a new x. Take the first m observations for both y and x, take them, make a separate data set. From this data set, what we will do is we will learn the regression coefficients. We will fit our linear regression model. The second part, which we'll call the test set, we really only use x and y, and we plug in the regression coefficients we learned in our training set and see how well those regression coefficients are at predicting the y in the test set from the x in the test set. So for a prediction question, first you want to just fit your model on the training data set, which we'll call f hat train. We'll want to build a set of predictions of the y test, the output test set, using your trained model with the new input x test. And then evaluate your test error using some model evaluation term. Notice this is fundamentally different than asking whether or not a term belongs in the model. What we're just asking here is how well does the model predict unseen future values. Now, in the context of the inference problem, how you set up your model has a huge impact on what you take away from it. Let's consider this in the context of an example. Let's say you have an empirical question. Are there gender differences in reading comprehension? So you run an experiment where you collect scores on a content recall task, which we'll call Y-read, and you just record each participant's gender. So in this case, we'll just use male and female. So for this, you would just want to fit a regression model Y-read equals beta naught, the intercept term, plus beta 1 times gender. But how you specify your qualitative predictor variable, in this case x, determines how you interpret the effects. So for example, you could designate gender using what's known as a dummy variable. In this case, 0 for male and 1 for female. If you define x that way, and you want to understand the mean effect of reading comprehension for men or males versus women, female, you just look at the intercept term, captures all the variance for males, and the beta 1 captures all the variance for females. Pretty intuitive. However, let's think of an alternative scenario where you coded gender using -1 for male and 1, +1, for female. Now, the intercept term doesn't map to maleness, and the beta 1 doesn't map to femaleness. Instead, male effects are beta 0 minus beta 1, and the female effects are beta 0 plus beta 1. In order to understand the mean effect of each one of these conditions will dramatically depend on how you code your dichotomous variables, your qualitative variables. Now, it's going to make sense and make your life easier to rely on this binary 0-1 coding scheme for these types of categorical variables, even in the context where you have more than 2 levels. So, for example, let's expand out the term gender to be male, female, and individuals who identify as non-binary. How would we create binary variables in our coding scheme to capture all 3 conditions? Well, in this case, the dummy variables would be one variable that just indicates whether or not a participant identifies as female. So it's 1 if they identify as female, 0 otherwise. We would add in another term, a different X term, which we'll call non-binary. In this case, it's 1 if the individual identifies as non-binary, 0 otherwise. Now we would fit a regression model that looks like this. The reading comprehension score y-read equals beta hat 0 plus beta hat 1 times the female variable plus beta hat 2 times the non-binary variable. I can capture all 3 levels of the gender category in this model. Male effects are represented by beta hat 0. Female effects are represented by beta hat 0 plus beta hat 2. And the non-binary effects are represented by beta hat 0 plus beta hat 1. So you see, you can have many levels to a categorical variable. The art is in breaking them up into separate binary variables and understanding how to interpret the fit regression coefficients in order to reveal the effects of each underlying category. Many statistical tools, including R, will automatically do this for you for categorical data. It'll turn it into binary data. It helps to do this automatically in your original data table itself. That way you have a little bit more control over knowing which variables are which. Now, using binary predictors as dummy variables are important in terms of inferring main effects. Let's also look at the context of how to infer from interactions. Remember, at previous lectures, we talked about how linear regression can do many of the things that specialized statistical tools like ANOVA and t-test can do. In our examples that we've used in prior lectures, we focused on ANOVA with just one variable with multiple levels. But what happens if you have 2 different variables with multiple levels? You could still look at interaction effects and main effects using linear regression. So for example, let's ask the question, does gender influence the effect of age on reading comprehension? So we're going to take the same reading comprehension score. We're going to stick with our binary male-female gender identity variable. And we're going to include now a continuous variable of age. So our model, if we wanted to look at the effect of age, the effect of gender, and the effect of age on gender, would look like this. We would have one main effect term of gender, in this case beta hat 1 times the gender term. We would add in a main effect of age, which is beta hat 2 times the age term. And when we create an interaction term by multiplying the gender identity term with the age term and include that new variable in our regression model such that the regression coefficient beta hat 3 represents that interaction. In a simple 2x2 design, we have an interaction between our two variables and their main effects. So this is a nice clean way of understanding how variables relate to each other in a more complicated way. However, if you're looking at interactions in regression models, you have to abide by the hierarchical principle. The hierarchical principle states that when including interaction terms, always include the main effect terms in the model. If you're including an interaction between x1 and x2, you always have to include the main effect terms for x1 and x2. If you have a three-way interaction, you have to include all three main effects, four-way interactions, etc. Why do we need this hierarchical principle? Well, let's do a thought experiment here. Let's say that I have a regression model with an interaction term. So x1, x2, and then the interaction term x1 times x2. Let's rewrite this equation to just look at the combined x1 effects. So I can kind of configure things here such that I now have my intercept plus a term that includes beta hat 1, which is the main effect for x1, plus beta hat 3 times x2, wrap those into a single term, which I'm going to call beta hat 1 star, and multiply that by x1. So that becomes the modified regression coefficient that really describes the effect of x1. And then I have beta hat 2 x2 for the main effect of x2. This is the same equation as what I had before. But really what I'm doing is I'm trying to understand the entire effect of x1 by combining the main effect and the interaction term. So notice that this beta hat star depends on both x1 and x2 in order to describe the total relationship that x1 has with y. Essentially, it boils down to constraining the interaction term and compressing the interaction term in this way. If I then excluded that main effect term from my model, then the fit, it removes that portion of the variance explained by this new meta term. If I didn't include beta hat 1 in this model, this would be incomplete. And what would end up happening is my interaction term would contain both information about the main effect and the interaction. It would give me a false sense of the magnitude of the effect that x1 has in its relation to both x2 and y itself. So when including interaction terms, you always must include all the main effect terms. So far, we have gone over the ways you interpret your linear regression models and how you form that model can determine how you infer from it. Now let's move on to thinking about what are some of the pitfalls of using linear regression. What are some of the ways that linear regression as a tool can break down? Now recall that the fundamental form of a linear regression model is just a linear summation of x times your regression coefficients plus some noise. This leads to a closed form solution for all your regression coefficients. That's just plug and play equations, as long as they follow these assumptions, these four assumptions. Violations of these assumptions, remember, break down how you can come to these closed form solutions for your regression coefficients. All of these are critical in order for the maximum likelihood estimate for the ordinary least squares problem to work. So let's look at how breakdowns of, or what types of breakdowns of these assumptions are critical for contaminating or influencing your results. First, you really have to watch out for outliers. In this case, outliers reflect a subset of values that violate the assumed sampling distribution of y. So let's say that I assume that y has a particular mean and a particular variance sampled from a Gaussian distribution, so this mu y and sigma y. If I have outliers that sit out here on the edge of the distribution, that violates that assumption of normality. And outliers can have a huge impact on not only the nature of the relationship between x and y, so the regression coefficients you fit, but also the reliability of using your model to predict unseen values of y. These outliers fundamentally break down the normality assumption that's necessary for assuming that your residuals are normally distributed. Now remember that the assumption is that y is normally distributed. We don't have necessary assumptions on the distribution profiles of any individual x. X can be binary, it can have odd distributional shapes. Those are fine in regression because overall you just want your residuals on y to be normally distributed. However, in x, you can have the problem of high leverage points. High leverage points are a subset of values in x that bias the outcome of f of x. These can be outliers, or they can be points that are not outliers in x, but as their relationship to y looks different. It almost looks like they're pulled from different, let's say, underlying distributions. For example, take a look at this scatter plot here. Again, I'm showing amount of sleep on the x-axis and digit span on the y-axis. Notice that there's this cluster of 4 points up at the top. These are high leverage points. Their position as a cluster is pulling up that regression line. The slope of that line is steep, not because of the overall relationship between hours of sleep and digit span, but because of the presence of this little cluster of points that are pulling that regression line up. Now you can monitor for high leverage points by calculating what's known as a leverage statistic, often summarized as the term H. A leverage statistic is the 1 over n, the number of points you have, plus the difference between any observation in x and the mean squared, over that same difference from all the other points that are not that value I. So you take out an observation, you calculate the deviance or the difference from that observation and the mean of x, and compare that to essentially the sum of all the other differences for all the other observations except the one of interest. What this means is that you calculate a leverage statistic for every unique observation that you have. So if we were going to run a leverage statistical analyses, often what you do is you plot the leverage statistic, which I'm showing here on the x-axis, against the x values themselves. And they pretty clearly point out cases, as you see in the upper right of this plot, where there are individual points that are leveraging or pulling the distribution of x. They have this undue influence on the influence of x, which, remember, because this distribution of x, the variance of x, is a critical factor in the estimation of the regression coefficient itself, these will have a powerful influence on the outcome of that fit. This is unlike the outliers, which were shown in the previous slide, which simply break down the normality assumption of the residuals. Another way that you get this breakdown of the ability to interpret or work with linear regression models is when you have a strong correlation between 2 or more predictor variables in x. Let's consider the most extreme case of this. Let's say that I have this regression model with x1 and x2. Now, the way to make x1 and 2 highly correlated is to make them equivalent. So let's just say I generated x2 by duplicating x1. So their correlation is going to be a perfect 1. This means that I can substitute x2 for x1. So now I have a case where I have equivalently duplicated x1 in my model. which means that I could rewrite this equation so that I sum the two regression coefficients, beta 1 and beta 2, together. I'm going to call that my new regression coefficient, beta 1 tilde. Beta 1 tilde captures the overall variance from the correlated factors x1 and x2. Now, this is the extreme case, but you can imagine this is true how this works even with highly correlated variables like 0.8, 0.9 correlation coefficients. Essentially, what it means is that with increased correlation, those regression coefficients for the correlated variables are splitting their variance. They're sharing variance. Here, beta 2 and beta 1 are half of what the actual regression coefficient is. So having the duplicate x1 in the model as being a highly correlated, x2 being a highly correlated version of x1, essentially I have half the effect for beta hat 1 and beta hat 2, whereas the real effect is this beta tilde 1. As you decrease the degree of correlation, this shared effect size breaks down, but you can see how it contaminates the way you infer the magnitude of the effect for correlated regressors. Now you calculate out the variance inflation factor for any pair of variables. This is VIF for short. The VIF is relatively simple. It's 1 over 1 minus the R square of any variable j with any variable that's not j. The closer to 1 that this R squared term gets, the more likely that the correlation is impacting your fit f of x, or f hat of x. So you can come up with a quantitative estimate, even if you have a mild degree of correlation between your x variables, you can come up with an estimate of how much that's inflating your variance, how much that's causing this, coupling of your supposedly independent regression coefficients. This doesn't mean that you have to throw away partially correlated factors. And we will go over later in a separate lecture how we can actually take advantage of this shared variance effect to gain some deeper level understanding about the relationships between x's and y's. Using the VIF just gives you the sense of how much that's impacting your overall model fit and is important to monitor. So the takeaway from this lecture should be that interpreting linear regression models depends critically on how they are set up and how closely the data aligns to the assumption of the fitting routine, in this case the maximum likelihood estimate over the ordinary least squares problem. In the linear regression lecture, I made a strong case for why ordinary least squares regression is an elegant, powerful tool. That is true, but interpreting it requires a careful understanding of how you constructed it and how closely your data fits to those assumptions. Violations of those assumptions or a lack of understanding of how you critically set up your model can fundamentally impair the ability to infer or even predict from any learned ordinary least squares regression fit.